All right, so welcome back. We've survived a week of online lectures. Congratulations to you. All right, so we ended last week by introducing the idea of Chapter 7, where we're going to look at the energy principle now with extended systems. So now that we've introduced that concept, let's start building things forward. So to do this, we need to go back to springs. So in Chapter 4, we introduced this ball spring model of how we think about matter. So we need to, we think of matter as being the series of interconnected masses all vibrating on springs. And we can use this model to think of how objects have energy within themselves, because the spring clearly has energy. It's moving, it has kinetic energy, and we'll see soon that it also, of course, would have potential energy. So to set this up, so we want to go after the kinetic energy of a spring system is obvious, so we want to go after the potential energy of a spring system. So to make this a little bit easier, so whenever we set up thought models in physics, we like to work with nice ideal systems. So we need an ideal spring. Now this ideal spring, it never grows weary. It can be stretched infinitely without being broken. It can be compressed infinitely. It pays its rent on time. It is just the perfect spring. No energy dissipation ever. All right, so because once you make a model work with an ideal system, you can then make the updates for, reality. Okay, so perfect in every way, just like Mary Poppins. Okay, so the ideal spring, we know that the force on the ideal spring system, F sub S, is equal to minus K sub S. Of course, I have written out the scalar force expression. All right, so to determine the potential associated with spring force, we need the negative gradient. So those of you who are in the calculus class, this is important to understand. For those of you in the algebra class, it's important to know where things come from. So I would not ask you to do this derivation if you are just in an algebra-based class. So minus du sub s ds must be equal to minus ks s. So by definition of the negative gradient. So we see that we have minus signs on both sides, therefore du ds is equal to ks s. And the question we need to ask ourselves is, what function has a derivative that looks like this? Ks, or k sub s times s. And so the answer to that is 1/2 k sub s squared. Take the derivative of that, you get this back. Okay. And this is, of course, the ideal spring potential energy. So u sub s is equal to 1/2 k sub s times s squared. And of course, k sub s is the spring constant and s is the amount of stretch. Remember, stretch is the absolute value of the difference of the relaxed length versus where it is now. So it does encompass both stretch and compression. So S is stretch measured from equilibrium. Which is, of course, the relaxed length. And then when we talked about the analytical solutions for the spring system, we often put the relaxed length at the origin. Okay, so the potential energy plot of this system looks like this. So we have stretch on X, energy on Y, so the more stretched it gets, the more potential it has, and it has the least amount of potential when it is relaxed. So if I've got my spring here, there it is, I've increased the potential, and now I am decreasing the potential. Of course, I'm pretending that is an ideal spring. Okay, so if you are dealing with an ideal spring setup, there's a couple features that it will have. So as the stretch gets large, and we'll see that these ideal concepts do still apply in less than ideal situations. As stretch gets large, U becomes infinite. Instead of approaching zero. I mean, after all, this can stretch forever, so. So secondly, for a system of a mass and ideal spring, all states are bound. You're not breaking free of this one. It can stretch forever, so how could you ever become free? So no unbound states. Now, of course, this does not describe real springs. They do get tired, they've got friction, they dissipate energy, they can break, they can become warped from being overly compressed. But it gives us an ideal of what the potential energy is going to look like for a real spring. So, one correction for a real system could be an offset. So for example, US is equal to 1/2 KSS squared minus ES, where ES is basically an offset from where the potential energy is going to start. So in this case, you'd have stretch, energy, and now your US does not start at 0, it starts here. And so this equation then encapsulates this offset for that particular system. Okay, so let's look at energy in oscillation. So what we're dealing with here is we've got a spring, we've got a mass, and you set it in motion and it's oscillating. It's going, it's a vertical system, up and down and up and down. All right, set that off to the side so that I can bring it back to play. All right, so let's examine this system on a fresh sheet of paper. So here is where we might do a little bit of back and forth class banter. I'm not as funny when I banter with myself. Actually, I'm not really sure I'm funny when I banter with you all, but I certainly enjoy that a lot more. You guys are very much missed. All right, so when we have a spring mass system and it's oscillating, so it's going up and down, or in the case of a horizontal system, it's going back and forth. What is happening to the kinetic energy of the system? So let me get this spring in motion again, so we can see that it's getting faster, it's coming to a stop, and then it's going the other direction. So the kinetic energy, try not to bump my notes there, is constantly changing. It's getting faster, it's slower, and then there's points where it has no kinetic energy. And these points are, of course, when it is at the end of the stretch, it has to stop, and then it will come back. And then it will stop again, and it will come back. Just like that. So the kinetic energy, K, is increasing and decreasing according to the oscillations. So we have noted that it is 0 at the ends. So that is specifically the places of max amplitude. And if it's 0 at the ends, K is the largest, because V squared is the largest in the middle. So it's going to speed up and speed up and speed up until it reaches the relaxed length. And then it's going to begin slowing down on either end. Okay, so now that we understand the kinetic energy, let's think about the potential energy. So it will also be increasing and decreasing. After all, energy is still conserved. So if there is nothing to work on the particular situation, which is certainly true if you have a horizontal spring system, then if the kinetic energy is increasing, by conservation of energy, we know the potential energy must decrease. And likewise, if kinetic energy is decreasing, potential energy must increase. So, and potential energy is going to be the largest at the ends, the places of max amplitude, and 0 in the middle. So also think both in terms of energy conservation, but in terms of the equation, potential energy of the spring depends on S. So S is going to be biggest at the place of max amplitude, and stretch is 0 in the middle. The spring is at its relaxed length. This spring here has no potential energy in this relaxed state. Okay. Okay, so now let's look at a horizontal spring system attached to a wall. I'm going to get a fresh sheet of paper so I don't bump into the bottom here. So we've got our spring system. Here is our wall. Let me bring in some pretty colors. Here's our spring. Let's put a mass on it. Make it green. All right, so this is going to be free to oscillate back and forth. There is some frictionless surface that it's on. So there's going to be no force contribution from that surface. All right, so the question I have is, would the wall do work on it? On the spring mass system. Okay, so we know the wall is applying a force. So the whole system is the spring and the mass. So we know that there must be a normal force coming from the wall. The question is that force doing work on it? Is there anything in the surroundings doing work on it? Okay, so let's set this up. So we have our spring plus our mass in our system. The surroundings, we have the earth, the frictionless surface that it's on, and the wall. Okay, so let's look at a force diagram. So we have the force from the earth, which is the force of gravity. It's going down. We have the normal force from the frictionless surface that it's on. Now the momentum could be going this way and it could be going that way. I've not told you what moment of time we're looking at, but the momentum is in the x-axis. Okay, so first of all, we know that neither the earth nor the surface that it's on is doing any work. Why? Because they're perpendicular. So Fn and F earth are perpendicular to motion. So 0 work. Now, we know that the force from the wall is, so that's F wall that I just put in, is in the same plane as motion. So let's deal with that. Now you're probably thinking, my gut tells me it's not doing any work on the system, but I don't know why. Or perhaps you're way ahead of me. You're probably way ahead of me. Let me give you more credit. All right, so the force of the wall times delta x is equal to 0. Because delta x is 0. The wall isn't moving, it's quite stationary. In fact, this symbol that I put here, these slashes, means we're dealing with a stationary object. So it's applying a force, but it's not applying a force over any distance. It's not changing momentum. Now, it's important to the system. If the wall wasn't there, so I'm not going to release the spring because I don't want to chase it. So if my finger here is keeping that spring in place, if it suddenly goes away, what's going to happen? It's just going to fling back that way. So the wall needs to be there, but it's not doing any work on it. It's applying a needed force, but it's not contributing work. So therefore, the only energy contributions are kinetic energy and potential energy, both of which we know how to deal with. So let's look at what these look like in a pretty little plot. Bringing it down. So we're going to plot energy flow, spring mass system. There it is. Okay, so we're going to look at this with respect to time. So we'll start out with kinetic energy. So kinetic energy, it's going to start off being, we'll say it starts off at 0. It's going to reach a maximum. It's going to go back down to 0 and make this nice little oscillating plot. Now let's look at our potential energy. So if it starts off at 0, we're dealing with a place of maximum potential. And so on and so forth. So green is potential and blue is kinetic. Now, if we were to add these two together, we would see that at any given moment, especially if I could draw a nice straight line, K plus U is going to be constant. It's a straight line. And of course, this just falls, as you, I'm sure, already anticipated, right out of the conservation of energy. This is a powerful, powerful fundamental principle. Well, all fundamental principles are powerful. And it makes sense. Surroundings do no work. Total energy must be constant. You don't get something for nothing. True with the energy principle, true in life. Okay, so just a couple quick asides. This is a nice example of path independence. Which we talked about in the last chapter. And then further, if we did have friction, and yes, you can do spring mass problems with friction, it would be in negative x when the momentum is in positive x, and F would be in positive x when momentum is in negative x, exactly as you would anticipate. All right, so we'll end our asides. And let's do an example. It's a big example, so I'm going to go ahead and get fresh paper. So we have a mass of 36 kilograms, and it's attached to a horizontal spring with a spring constant of 72 Newton meters. Friction is negligible. So in other words, maybe it's there, but we can't really measure it. So at t equals 0, the spring is compressed 5 centimeters, and the mass has a speed of 0.75 meters per second. Now we're going to use the energy principle to answer the following. What is the amplitude and what is the maximum speed of the block? Okay, so to solve this problem, we're going to use the same system and surroundings for both of these questions, but we're going to need to be clever about choosing our initial and final states. So remember, in physics, we are always trying to make solving a problem easier. So we're going to want to think about how to do that. Okay, so our system is going to be the mass plus the spring. Our surroundings, in this case, is going to be the earth, the surface it's on, the wall, and we're neglecting friction, air resistance. It's a fairly ideal setup. Okay, so for the first part, we want to go after the amplitude. So let's just go ahead and break this off to two sections. So we know that this is going to have the maximum amplitude when the speed is equal to 0, because that's right before it gets ready to turn the other direction. So max A at v is equal to 0, where v has no vector sign, so we're dealing with speed. So let's choose our initial state based on the information given to us in the problem. So the initial stretch is equal to 5 centimeters. The initial velocity is equal to 0.75 meters per second. The final state, since we want to go after max amplitude, so let's choose v final is equal to 0 meters per second, which gives us max amplitude. Also, zeros are fantastic things to find and put into your problems as long as they belong there. So let's set up our energy. So we know that delta E is equal to any work that's being done. We'll flesh that out further. We also know that E final is equal to E initial plus any work being done. So this is what we're starting from. So we have K final plus U final is equal to K initial plus U initial plus any work done. So where are my zeros at? Well, we've said that it has a 0 velocity at the final state. There's a 0. We've said that there's nothing in the surroundings to do work on it. There's another 0. Oh, look at how much easier that is. Beautiful. So using that, potential final is equal to kinetic initial plus initial potential. We can start plugging in our expressions. So 1/2 K sub S, S final squared is equal to 1/2 MVI squared plus 1/2 K sub S, S I squared, where F's and I's, of course, are standing for final and initial states. Okay, so the term that we want is right there. But let's go ahead and do some solving first just to make it a little bit easier. So one of the calls you'll have to make is when to plug in numbers. I'm going to show you what I think tends to be the easiest way to plug in numbers with the least chance of error, but recognize that you can do these steps in a variety of correct orders. So if you wanted to do all the algebra first and plug in at the end, that would be fine. You just need to make sure that you're really keeping track of your algebra. You could also decide, well, I know all the values on this side, so I'm going to solve for this number first, and then algebraically manipulate that side, which is what I'm going to do to solve this problem. Okay, but both would be correct. So 1/2, our mass was given, it's 36 kilograms. The initial velocity is 0.75 meters per second quantity squared, plus 1/2, the spring constant is 72 newtons per meter, times the stretch of 0.05 squared. Remember, it was centimeters, so we have to convert that into meters. Okay, so we have, if we plug all those numbers all the way through, we have 1/2 K sub S, F final, stretch final squared, is equal to 10.22 joules. Okay, so we see that S final squared would then be equal to 2 times 10.22 joules divided by K sub S, and then we'd want to take the square root of both sides. So our final stretch is equal to the square root of 2 times 10.22 joules divided by 72 newtons per meter. And so final stretch is equal to 0.53 meters. All right, so we've figured out the max amplitude. Now we need to go after the max speed. So we want max speed. We are taking it to the max in this problem. All right, so we're going to use the same system and surroundings. So our system remains the the mass spring, and the surroundings has nothing of interest. Nothing to do work on it. And that's really the question. Is there measurable work? Okay, well, there's nothing of interest in your surroundings. So the initial state is going to also be the same. It's given in our problem, so we're just going to use it. So our initial stretch is 5 centimeters or 0.05 meters. And our initial velocity is equal to 0.75 meters per second. Now, the final state, we want to be a little bit clever once again. So we want to look at where the stretch is going to be equal to 0, because that is where the kinetic energy is maxed out. So when it returns briefly to its relaxed length, that is where we want it. So we want the stretch final to be equal to 0. This is where V is equal to the max. Also, another nice little 0 that we can add in, because zeros make our lives easier. So this is the setup we're going to be using as we set up our energy principle. So once again, E final is equal to E initial plus any work that's being done. Let's flesh this out. Kinetic energy final plus potential energy final is equal to kinetic energy initial plus potential energy initial plus any work done. So where are my zeros at? All right, so we know work is 0. There's nothing there to do any work on it. Now, we know that the original potential is non-zero. This is non-zero, but we have set it up so that our final state is at when stretch is 0, so therefore our final potential is equal to 0. So look at that lovely and much more easy equation. So K final is equal to K initial plus potential initial. Now, because of how we chose to solve our previous problem, we know this is equal to 10.22 joules, so from previous. So since we know it, let's use it. So we have 1/2 mv squared final is equal to 10.22 joules. So let's solve for V final. V final is equal to the square root of 2 times 10.22 joules divided by the mass. V final is equal to 2 times 10.22 joules divided by 36 kilograms. V final is equal to 0.754 meters per second. All right, so that ends part 1 of week 13, Monday's lecture. I will see you back for part 2.